Hey guys, welcome back to another week of e-learning. Today we're going to be talking about pH, and just to give you a general idea about pH and to kind of review what you might already know, and we'll get into notes here in just a second. But just wanted to kind of show you, this is from the PhET website, kind of a visual of pH. So if you look over here on the left, you see the scale. The bottom part of the scale is acidic. So anything that has a pH of 0 would be extremely acidic. Anything that has a pH of 14 would be extremely basic. And technically, you can go above and below that. So in other words, you can go above 14 and below 0, but it's very difficult to do. It takes a really high concentration of acid or base. Most of what we're dealing with in solutions, meaning like the pH of, let's say, the water in the Mississippi River, or the pH of drinking water, or the pH of pool water, or the pH of your blood, or the pH of tomato juice. We're talking about stuff that falls in between the 0 to 14. And when it comes to water solutions, most of the time it's near 7, which is neutral. This is pure water. So if I hold this little pH probe over over the little tank of water, it's going to read a pH of 7. We can try some other solutions, like let's say I got some gross stuff on here, like spit and vomit and stuff like that. But let's just say we're talking about milk, all right? So it's going to give me a pH of 6.5, so slightly on the acidic side of things. Whereas, I don't know, let's go with hand soap is going to give me a pH of 10, so pretty basic. And we're going to talk about exactly what that means a little bit more in a little bit more detail. Okay, so the first thing I want to say is that the the CK12 stuff takes you into a little bit more depth than we need to go into in terms of some of the math, but we do need to understand the basics of this. So the first thing we have to understand is that pH represents the concentration of, if you remember, hydronium is what that symbol means, in a solution. So what does concentration mean? Well, another name for concentration is molarity, and it's simply a measure of the number of moles of dissolved substance, or solute, you may have heard that term before, per liter of solution, or divided by liters of solution. So what does that mean? It means if you have, let's say, sugar water, and you have a glass of water, let's say we're talking about like Kool-Aid or something, or just for whatever reason you're dissolving sugar in water, um, some of the sugar is going to disappear unless you put in too much, but for the most part it's going to disappear, and those particles are going to be spread out throughout the water solution, so much so that you can't even see them. They're dissolved. They're surrounded by water molecules. So let's say this is a big pitcher of water that has a volume of 1 liter. Um, so if this is 1 liter, and let's say in that 1 liter we have enough particles to give us, excuse me, 0.5 moles of sugar. And if you remember what moles means, we talked about this with gases, but it's been a little while. Moles are just a counting unit for particles. So because atoms and molecules are really small, we group them together not in dozens like you would for eggs or roses or donuts, um, or into centuries like you do for years if you're talking to a historian. A counting unit for atoms and molecules is got to be really big, and it's 6.02 times 10 to the 23rd, but that represents a mole. So zero point 0.5 moles of sugar, it sounds like a small number, but it's actually a lot of sugar molecules. Okay, so if I wanted to know what the molarity of this is, I simply take my moles of sugar, which in my example would be 0.5 moles, and I divide it by my volume of solution, which was 1 liter. And so, of course, 0.5 divided by 1 is 0.5. and I give it the symbol capital M, and that stands for molarity. Okay, so that's a simple explanation of concentration, but basically it's just how much stuff is crammed into a given volume. Okay, so what does this have to do with pH and acids and bases? Well, the first thing we have to do is understand that water self-ionizes. So when I have two water molecules and they bump into each other inside a glass of water or tea or, you know, in a lake or wherever we find water, when these guys bump into each other, what actually happens is a very small amount of the time, there's a reaction that happens. We call it the self-ionization of water. And essentially what's going to happen is one of the hydrogens from one of these waters is going to get transferred to the other one. So when that happens, on the other side of the equation, what I end up with is one water molecule that now has an extra hydrogen. So here's my water molecule that now has 3 hydrogens. And because that hydrogen that did that jumped over from one to the other, left its electron behind, this particle over here is now going to have a +1 charge, and it's also known as hydronium. So that should be familiar to you. Now, what's left behind of our original water molecule that lost its hydrogen would just be OH minus, oops, I guess I'm drawing pictures. Sorry. So an oxygen and then just 1 hydrogen left behind, and it would have a minus charge, and of course that's our hydroxide. So this process that I just described is called the self-ionization of water. And so if I write it in equation form, these two water molecules would simply be represented as 2H2O, and then what that gives you is, of course, a hydronium and a hydroxide. In any sample of water, it could be my cup of coffee here, could be a bottle of water, the ocean, it doesn't matter. There's a small percentage of water molecules at any given time that will have turned into hydronium and hydroxide. And it's a very small amount, but it's significant. And the thing you have to understand about this reaction is it's actually reversible. So once the hydronium and the hydroxide meet up again, they can actually turn back into water simply by transferring that hydrogen back. But there's always going to be some in any sample of water. There's going to be a small amount of hydronium and hydroxide because of this process. Okay, and so what I want you to notice here, guys, is because this is a reversible process, if I have a substance that has more hydronium, that is going to mean, by definition, it's going to have less hydroxide. And the reason for that is because if I look at this reverse reaction, adding more hydronium is actually going to speed up the reverse reaction. And that's because there's more collisions between hydroniums and hydroxides. Because if I put in more hydronium, there's going to be more opportunities for hydronium and hydroxide to come together to form water. Well, what is that going to do to the concentration of hydroxide? If I put in more hydronium, so let's say we have an acidic solution like soda, and so therefore it has more hydronium in it than pure water does, that extra hydronium is going to react with some of the existing hydroxide and use it up. So whenever the hydronium goes up, the hydroxide goes down. They're both really small numbers in most solutions, especially something like soda that's pretty close to neutral, or not too far from neutral. So they're both really small numbers, but as one goes up, the other one has to go down. Let me show you on the PhET demonstration what I'm talking about. So let me just move myself here out of the way. There we go. Okay, so this is neutral water, pH of 7. If I change it to a solution that has an acidic pH, what I'm really doing is adding more hydronium. So I'm going to slide on the left there. You see me sliding up that hydronium? And you can see the little dots in the water. The red dots represent hydronium and the blue dots represent hydroxide. So do you see by sliding that hydronium up just a little bit, the actual numbers, the concentrations are still really small for both of them. But if you look at the number of dots in the solution, by adding just a little bit of hydronium, the hydroxide went way down. Let's bring this back to, oops, didn't mean to do that. There we go. Let's bring this back to neutral, back to 7, and see again what it looked like. So at 7, there was pretty much the same number of blue and red. But by adding more of the hydronium, very quickly the blue starts to go away and the red starts to show up. Now their concentrations are still very, very small. Remember my sugar water example, my concentration was 0.5. Well, these are like 6 times 10 to the negative 7, 1.7 times 10 to the negative 8. Really, 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 really small concentrations, right? So let's take a look at a little bit of math with these two, okay, or with the concentrations. So if you remember, hydronium and hydroxide were both really, really small numbers, all right, in pure water. Their concentrations are actually both 1 times 10 to the negative 7 molar in pure water, and they're equal to each other. And so because as one goes up, the other goes down, we have this equation called the ionization constant for water. And all it means is that if I look at the concentration of hydronium times the concentration of hydroxide, and the little brackets mean concentration of, I will always get the same number. And because these are both 10 to the minus 7, if I take 10 to the minus 7 times 10 to the minus 7, I actually get 10 to the minus 14. And it gets molar squared as its unit because molar times molar would just be molar squared. Okay, so that number always stays the same. So let's take a look at a problem like what you saw in the CK12 assignment. Okay, so this problem says, what is the hydroxide concentration of a solution which has an H plus of 1 times 10 to the minus 5? So, and this just, the H plus is the same thing as H3O plus, okay? So all I have to do is know that hydronium times hydroxide always equals 1 times 10 to the negative 14. And so what they're doing is they're giving me one of those numbers to plug in. It's giving me the hydronium is 1 times 10 to the minus 5. So I'm going to plug that in right here. So 1 times 10 to the minus 5. And I don't know what hydroxide is, so I'm just going to kind of put that there. And then I'm going to say it all equals 1 times 10 to the minus 14. Okay? So what would you do to both sides to get hydroxide isolated? Right? So you should have said what you would do to both sides is you would divide by hydronium, right? You would divide by 1 times 10 to the negative, 1 times 10 to the negative 5. All right? So that takes care of the 1 times 10 to the negative 5, and it gives me hydroxide by itself. So the only thing we have to do now is get out a calculator. If you don't have a scientific calculator, you can do this on your phone, on just about any phone. But let's go ahead and so, yeah, here we go. Oops, sorry. Home button's a little broke here. All right, so here is, this is like on my iPad. I tried to download one that looks just like an iPhone, if that's what you happen to have. Oops, let me move myself again. Okay, so clear that out. So let's take a look at the math that we were doing. So we had 1, and then we had EE to mean times 10 to the negative 14. So I'm going to hit 14 negative divided by, and it turns it into regular notation. And then let's see, what was our other number? Oh, 1 times 10 to the negative 5, right? So we're going to go divided by 1 EE 5 negative and hit equals. And we get, if I count over here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this looks like 1 times 10 to the negative 9. And let's see if that was one of our answer choices. So 1 times 10 to the negative 9, and that is molar, and yes, that was answer choice C. Okay. You're also given a question like this one. I'm not going to worry too much about this one. There's actually a fairly simple way that we can do this, but just in the interest of time and what I think is most necessary for you to understand, we're going to skip over it. And if you missed it on the, or if you had trouble with these on the in the CK12, don't worry about it. Obviously, at this point, you guys realize you just have to keep going until you get 10 right, and then you get credit for the assignment. So if there's a few questions in there that are a little bit tougher than what I want you to know, shouldn't be too big of a deal. Okay, so let's talk about pH. The pH scale ranges from 0 to, I'm going to stop at 7 for a second, but it actually goes all the way to 14. And down here is acid. Up here is base. Okay, so if it's above 7, it's base. If it's below 7, it's acid. And if it's right in the middle, of course, it is neutral. There are very few things, including most drinking water, that are exactly neutral. It's very tough to do that. But to find pH, it is simply going to be the negative log of hydronium. So if you haven't had logs yet in algebra, it's not a big deal. All we really need to do is know how to put this into our calculator. So if I get a pH of, or sorry, if I get a hydronium concentration, let's use the last problem that we did. The hydronium concentration, the last problem that we did was 10 to the minus 5, right? Or 1 times 10 to the minus 5. So let's talk about converting that into a pH to see whether this is acidic or basic or neutral. All right, so if the hydronium is 1 times 10 to the minus 5, how do I take the negative log of that on my calculator? Right, and by the way, if you have had some logs, logs have bases. And in this case, it's log base 10, but that's, you don't really have to worry about that on most calculators because your calculator is just going to assume that it's log base 10. And again, I don't expect you to conceptually even understand what a log is, but I do need you to be able to calculate pH, and that's why I'm showing you this. Okay, so let's see if we can take the negative log of 1 times 10 to the minus 5. All right, so on the calculator, see if we can do this, clear out our last problem. Okay, so on my calculator, I'm going to hit 1 EE5 negative, and that's going to just turn it into regular notation. Okay, and then I'm going to hit the log base 10, and then I'm going to take the negative of that, and so I get 5. All right, so that's how we use the calculator to find, at least the calculator on your phone or other device that you might have. That's how we're going to find the pH. So again, all you do, it's the log base 10 of your hydronium concentration. So on this calculator, I'm going to put in the hydronium concentration first. So it would, for our problem, it was 1 EE5 negative, and then I'm going to hit equal, okay? And that's just my hydronium concentration in regular notation. And then I'm just going to hit log base 10, and then I'm going to take off the negative sign. That's all I have to do to find the pH of a solution. Okay, so that means my pH for this problem equals 5. And so that's going to fall somewhere here in the acidic part of the scale. All right, so let's try another one. See if you can find the pH if the hydronium concentration equals, let's say, 1 times 10 to the negative 9 molar. Okay, so you should have taken the negative log of 1 times 10 to the negative 9, and that actually gives you 9. And I'll show you how I did it on my calculator. All right, so clear out the last problem. I'm going to do 1 EE9 negative. gives me a really small number because that's what it is. It's a really small number. And I'm going to hit log base 10 and then just take off the negative sign. And there's my answer. Okay? So that's how to calculate pH from hydronium. Let's look at one, oops. Let's look at one more thing here. I want to look at the PhETS simulation so you can just kind of see what this looks like for real substances. So if I look at, let's go back to, we got water. You can see the hydroniums and the hydroxides are more or less equal here, right? The red and the blue. If I go ahead and change this into, let's say, coffee, you can see that the red has gone way up and the blue has gone way down. In the picture, there's only 2 dots. In reality, of course, there would be a lot more molecules, but there's still a really low concentration of hydroxide and a much higher concentration of hydronium, which is why this is acidic. The pH scale is actually logarithmic. And so what that means is for every 1 pH that I change, I'm changing the concentration of both hydronium and hydroxide by 10 times. So a huge change in the actual number of hydronium ions, you can see there's a lot more red here than there was before with water, results in what looks like a relatively small change in the pH. So by changing the pH from 7 to 5, it's not that my pH only changed a little, it actually changed by 100 times, or 10 to the second power. Okay, so it's logarithmic. It's sort of like the Richter scale with earthquakes, if you've ever heard of that. So an earthquake that has a magnitude of 5 is not slightly more powerful than one that has that registers a 4 on the Richter scale. An earthquake that is a 5 is like 10 to the 5th power compared to 10 to the 4th power. So it's actually 10 times more devastating than that 4 on the Richter scale earthquake. So the pH scale works the same way. So in order for me to go to something that's, let's say, really, really basic, like drain cleaner with a pH of 13, you can see there's almost no hydronium in there whatsoever. It's like almost completely hydroxide. The hydronium count is really, really small, 1 times 10 to the negative 13. So hopefully that makes a little bit of sense to you. I'll put the link to this PhET simulation on Classroom as well, so you can kind of play around with it yourself if you want to. There's no points associated with that, but if you're curious about how this whole pH thing works as a function of hydronium and hydroxide and what the picture looks like, you can kind of play around with that. It is an HTML, so you can do it on your phone or your tablet or your Chromebook. So, all right, well, that's it for pH, and we will see you guys next time.